Okay, so this problem is related to the relative velocity. To define relative velocity, let us consider three reference frame: frame C, reference frame B, and a reference frame A. Okay, so suppose that this C is in motion in the reference frame B, and this reference frame B also by itself in motion with respect to A, and A is at rest. So how velocity of C looks like from the reference frame of A? The velocity of reference frame C will be somehow related to the reference frame B, because she is within the reference frame B and B is itself moving with certain velocity, and within B, reference frame B, she is moving. So velocity of C is related to velocity of B. So this is said to be relative velocity. In general, when observer is at rest and some particle, some object is moving, then we simply call velocity. But in this case, we call relative velocity, because the velocity of this C, reference frame C, is somehow related to reference frame B. Okay, uh, let us go back and read this question. Right here in this question, an airport walkway moves at 3 mile per hour. Suppose that this is the walkway, right? This is moving with 3 mile per hour, right? In this walkway, this is the walkway. There is a This is a walkway. Within this walkway, uh, there is a passenger. A man walks at a leisurely pace of 2 mile per hour. So here is a man. He is moving with a velocity of 2 miles per hour, right? Within this frame itself is moving, right? Airport walkway is moving, and within that airport walkway, a passenger is walking with 2 miles per hour. Look at here. Airport walkway itself is in motion, which is 3 mile per hour, 3 mile per hour, and this guy right here is also moving within the walkway with 2 miles per hour, right? And if some observer is here and looking the velocity of this one, this is the relative velocity, velocity of the passenger as seen from the rest frame of reference. The person who is just sitting on the chair will be different than the normal velocity that we call relative velocity. Okay, so let us define like this way. Let me symbolize uh, these velocities. First of all, let us say the velocity of passenger with respect to the walkway. Velocity of passenger with respect to walkway is 2 miles per hour, right? And velocity of walkway with respect to observer is 3 miles per hour, right? These are two velocities. So velocity of passenger with respect to observer is what? We have to calculate velocity of passenger with respect to observer. This is the velocity of passenger with respect to what? Walkway, which is 2 mile per hour, and this one is velocity of walkway with respect to the observer, which is 3 miles per hour. But if you look at directly from the observer's point of view, the velocity of passenger, it will be somewhat different. Okay, so to find the velocity of passenger with respect to observer, we can set off the formula. look at here. Velocity of passenger with respect to observer sitting on the side will be equal to sum of velocity of passenger with respect to w, which is walkway, plus velocity of walkway with respect to observer, right? So this will be 2 plus 3 is equal to 5 miles per hour. If both are moving in same direction, okay, what will happen if they are moving in opposite direction? Look at B. So this is for part 1. In part 2, if he walks on the walkway in the opposite direction as the walkway, what is his speed as seen from the ground? So in that case, part B, uh, vector reversed will be negative, so that I can write down this one like velocity will be negative for B. Just make it B. Velocity will be negative, and B, uh, velocity of 3 miles per hour. Okay, so using same approach, velocity of passenger with respect to the observer sitting on the chair minus 2 plus 3, which is 1 mile per hour, right? So if it is walking opposite direction, the observer sitting on the chair of the airport will see the passenger is walking with the velocity 1 mile per hour. Okay, so this is the one problem. So it may not be the case always. Suppose that suppose that